Okay, so lesson 10 is all about ionic bonds. And just before we went on break, the last really material we spent time on was all about electron configurations and where an atom is located on the periodic table and what that means as far as what energy levels its electrons are in and how it's going to behave. And so, as we begin our discussion on ionic bonds, we're going to take a moment to review electron configurations. Okay? And these will all look very familiar to you because we've spent time in class working with these before. But we're going to come up with the electron configuration for carbon, for calcium, for sulfur, and for iodine. Okay? We're going to come up with the electron configurations from this, and then we're going to take the next step and answer the question, so what? So what that the electrons are in these energy level, what does that actually mean? All right? Y'all ready? It's going to be good. It's going to be good stuff. All right. So here is the periodic table that we've used to assist us in coming up with our electron configurations. And so, correct me if I'm wrong, but I believe that carbon is located right here on our periodic table, which means that its electron configuration should end in what? 2p2, because this is a 2p section, and this is the second position in the 2p subshell. So our electron configuration should end in 2p2. And by this point, you all are budding chemists, and so you know that if you're going to start putting electrons into an energy level, you need to fill lower energy levels first. That's how it works. So if we're going to start putting electrons into this 2p subshell, we better fill the lower energy orbitals first. And the lowest energy orbital is what? 1s. And how many electrons fit in a 1s subshell? 2, because it contains one orbital, and one orbital holds 2 electrons. And then immediately after 1s comes 2s, reading left to right, top to bottom. 2s, and how many electrons fit in a 2s subshell? 2, because it is still an s subshell, which contains one orbital, and one orbital contains 2 electrons. Okay? Right? And so we're done as long as our total number of electrons match. So we've got 2 electrons in this orbital, plus 2 more in this orbital, plus 2 more in this orbital, which makes a total of 6. And if you look at the atomic number for carbon, it is 6, which means that if it is an uncharged version of carbon, it should have as many electrons as it does protons, and that number should be 6. Okay? Cool? All right, and now calcium. Correct me if I'm wrong. The calcium, I believe, sits right here on the periodic table, meaning its electron configuration should end in what? 4s2. Let's give ourselves some space here. And again, you guys, and gal, you are budding chemists, and you know that if you're going to put electrons into an orbital, you have to fill the lower energy orbitals first, starting with
3p.
Starting with. I like what you did there. Starting with 1s, and we can put 2 electrons there. And then we go to 2s, and we can put 2 electrons there. And then what comes next? 2p, and we can put how many electrons there? 6. And why can we put 6 here? It's a p subshell, which contains 3 orbitals, and each orbital can hold 2 electrons. Okay? And we talked about this before we went on break, but you know that the 3 orbitals here are all equal in energy level. Okay? And so when you get to that situation, the electrons try to stay unpaired as long as possible. Okay? Because they're both negatively charged. Negative charges repel each other. Right? Negative charges like positive charges. Negative charges do not like other negative charges. Okay? Just like hamsters do not like other hamsters. Okay. I don't know if you knew that or not, but hamsters are solitary creatures. They don't like other hamsters. If they grew up with them, then they're okay, but if you try to introduce one later on, it's not good. My wife was like, oh, we should get another hamster. And I was like, you do not want to get another hamster because they will fight. And they'll fight to the death, oftentimes. Anyways, it's not pretty. Okay, so you know that. We've got 3 p orbitals here. They're all equal in energy. The electrons will stay unpaired as long as possible. But if we're going to fill it up, each one of them gets 2. Right? But where do we go after 2p? Reading top to bottom, left to right. 3s. And how many electrons go there? 2. And then where do we go? 3p. And how many electrons fit there? 6. It's still a p subshell, and every p subshell can hold 6 electrons. Okay? And now we're done, as long as what is true? That the total number of electrons accounts for the total number of electrons calcium should have. Okay? We've got 2 here. Plus 2 is 4. Plus 6 is 10. Plus 2 is 12. Plus 6 is 18. Plus 2 is 20. And if you look in the top right corner of calcium, what number do you see? 120, which means if it is uncharged, it should have 20 protons and 20 electrons. Okay? It's good stuff, right? Now it's time for sulfur. Again, correct me if I'm wrong, but sulfur, I believe, sits right here on the periodic table, which means its electron configuration should end in what? 3p4, because this would be 3p1, this would be 3p2, this would be 3p3, this would be 3p4. So its electron configuration should end in 3p4. And just like our previous elements, if we're going to start putting electrons into that orbital, we have to fill all of the lower energy orbitals first. Even having the door open, there's not enough airflow.
It's happy now.
What's that?
It's happy now.
It's happy now? It's still blinking, but it's not giving us a yellow. So we've got to fill all of these lower energy orbitals just like we did with calcium. Right? Those are the only orbitals that are lower in energy than 3p. Do you agree? And so let's count the total number of electrons and see if we are in fact done. We've got 2 plus 2 more is 4, plus 6 is 10, plus 2 more is 12, plus 4 more is 16, right? If you look at the number in the top right corner of sulfur on your periodic table, what number is there? 16, so we have accounted for all of our electrons. We know exactly which orbital every electron is in, which is really helpful for knowing how sulfur is going to behave chemically. All right, and finally, iodine. Correct me if I'm wrong, but I believe iodine sits right here on the periodic table, which means its electron configuration should end in what? 5p5. This is a big one. Let's give ourselves some space. 5p5. And what are we going to have to do if we are going to start putting electrons into this subshell? What do we need to do? Fill every lower energy subshell first, starting with 1s2, then 2s, then 2p, then 3s, then 3p. And this is where it gets interesting. Then 4s, but then before we get to 4p, which has been our pattern, we have 3d sitting there, right? Reading left to right, from 4s we go to 3d, and this was always frustrating to me. It's not so much now because I feel like I've accepted it, but 3d, that subshell, is higher in energy than 4s, and it's because of just the sheer size of a d subshell. Even though it's a lower energy level, it's a very big type of subshell. Okay, so after 4s2, we go to 3d. And how many electrons can fit in a d subshell? 10. And that's because there are 5 orbitals, but we could check that just to make sure and count the number of elements listed here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 8.
Sorry if I didn't listen, but why does it say 3p4? Because then up top it's 3p6.
Right here?
Yeah. But then,
Oh, 3p4 because we couldn't completely fill this one, right? Because its position was here. To completely fill it, we would have had to be here. So we didn't quite get enough to completely fill it. So on the one that you end in, it's oftentimes going to have fewer than its capacity because you just don't have enough electrons to fill it, right? You only have to completely fill it if you're going to start putting electrons at a higher energy level. But if you're not, you can only put as many electrons as you have, right? Does that make sense? Yeah. Like I would love to fill every bowl in my house full of ice cream. But I got a lot of bowls and not that much ice cream. Gosh, wouldn't that be awesome? But it'd melt before you even had a chance to eat it all. Then that'd be sad. So 3d10, then we go to 4p. And 4p, it's a p subshell, and we know we have to completely fill it because we have electrons in a higher orbital. So it's going to hold 6. Then we go to 5s. And that we have to completely fill because we're putting electrons at a higher energy level. And then we go to 4d. Sorry, that got a little crowded. Can you see those numbers okay? My 10 overlaps the 5 a little bit. Here. I got more space. 4d10, 5p5. And again, we have the same situation here, Aiden. If we were going to completely fill this, it needs 6, but we don't have enough electrons to do that. But we'd only have to if we started to put electrons into 6s. So we couldn't decide, hey, let's only put 4 here, and then put 2 into 6s. You can't do that. Usually. I mean, there are always exceptions to rules, but you can't do that because you got to fill this before you can start to go into a higher energy level. And now we're done as long as what is true. Total number of electrons are right. So we've got 2, 4, 10, 12, 18, 20, 30, 36, 38, 48, 53. When you look at the number at the top right of iodine, what is it? 53. And we know where all 53 of those electrons are. At least inside of one of these orbitals. Where they are inside that orbital, who knows? But they're somewhere in that orbital. And this orbital is pretty small. This orbital right here, huge. This orbital right here, even bigger. So, but to know that there are 10 electrons somewhere in there is helpful. But then as far as the atom is concerned, that is a huge amount of space. But you're like, Dr. Eagle, atoms are tiny. You're right. But electrons are way, way, way tinier than an atom. So, it's like when you're a kid, the play place at McDonald's seems enormous, right? Because you're tiny. And then you get to be an adult, which none of you are yet, and all of a sudden the play place, it's scary. Because you're like, if I have to go in there to get my kid, I don't know if I can get out, right? Just like when it's time to go and your kid's not coming, you send some other kid, like that you don't even know. You're like, hey kid, I need you to go find the kid in there that looks like me. Can you do that? And then they like stranger danger and run away. It's tough. It's tough. The life of a parent. It's hard. Love your parents because they work hard. Go give them a hug and tell them thank you. Especially if you get stuck in the play place at McDonald's and they come and get you. When was the last time you were in a play place at McDonald's? Has it happened in the last 5 years? Me either. I don't think. I had to go get my daughter because we only had one kid at the time, but she was less than a year old and she's almost 8 now. So that's how long it's been. But Billy B's, have you all seen Billy B's over at the mall? It's like a giant McDonald's play place. I've been on a couple of those slides, you know, no big deal. All right, any questions about this? Because now we've reviewed enough that we can move on and start to introduce some new concepts. What say ye? All right. So the first question we're going to deal with for lesson 10 on ionic bonds is this one. Why are noble gases so happy? Why are noble gases so happy? It's an excellent question. And you're like, they're atoms. Are they really happy? No, but they seem to be satisfied. And maybe that's really what happiness is for everyone, right? Just satisfaction. All right. So I need you to remember something we've talked about before, that all atoms want a completely filled p orbital as the highest energy level. That's what they want. That's what every atom wants. Why do they want that? I don't know. You can study quantum mechanics and give a somewhat good idea of why they want that, but it's just there's something about that that's wonderful. You can also study quantum mechanics and make an argument that a cat in a box is both dead and alive at the same time. So, I mean, what do we really learn from quantum mechanics? I don't know. Because very obviously a cat cannot be both dead and alive at the same time, whether it's in a box or not. But quantum mechanics tells us, no, it actually can be both dead and alive at the same time. Until you observe the cat in the box, at which point the cat has to make a decision to be dead or alive. Yeah. That is just quantum mechanics, man. It's strange.
So it's like if a tree falls in the middle of the woods and it goes around, sort of thing?
Yeah, does it make a sound? And that one's interesting because sound is really the way our brain interprets vibrations. So like, are the vibrations sound, or is it really only sound if your brain actually takes those vibrations and converts it into something you understand? I don't know. I don't know the answer to that question. It's pretty philosophical. This one's less philosophical and more just really strange, because really, really tiny materials don't behave according to Newtonian physics. So like Newton's laws do a really good job of explaining, if I throw my son into the air, how far will he fly before he comes back down to the ground, right? Newtonian physics do a wonderful job of explaining that. When you've got something the size of an atom, Newtonian physics do not explain atoms very well. They're just way, way too small. Newtonian physics also don't explain really large objects very well either, because they're too big and too complicated. So then you get quantum mechanics for really tiny objects, but it's so unnatural. It's just weird, like a cat in a box being both dead and alive at the same time. All right, noble gases, they already have this. And yes, I know that noble is spelled wrong here. Somebody pointed that out on Monday, but I like this misspelling, so I kept it. And I know it says Nobel gases, but then it made me think about the Nobel Prize, and I smiled, so I left it. That is not the correct way to spell noble. But noble gases, they already have this. They have a completely filled p orbital as their highest energy level. So what this typically does is it makes for typically 8 electrons in the highest energy level. And so let's take a look at, let's say for our purposes, we had this electron configuration. Okay, so it wasn't calcium, but we had this electron configuration. So this would be a noble gas because it has a completely filled p subshell as its highest energy level. Would it be xenon? Is that what's in 3p6?
I think that's krypton.
Krypton. So it'd be krypton. Is xenon next? Is xenon 4p6? Okay. And then above krypton, is that neon?
No.
Argon? And then above that is it neon?
Yeah. Actually, I think it's
Oh, I was.
Yes,
argon.
It was argon.
That is argon.
Okay, this is argon. Argon is 3p6. Okay, all right. So this would be a noble gas, and its highest energy level is 3. Do you see that? Highest energy level is 3. There are 2 electrons in a s orbital and 6 electrons in a p orbital, for a total of 8 electrons in the highest energy level. Yeah.
Actually, I'm pretty sure it's krypton because I think you don't count helium as one of the p.
Well, the thing is, this says 4p.
But
it starts at 2p.
so yeah, so it does start at 2p. The first time we get a p is in 2, so this one would be 2p and then argon would be 3p. But now let's do this. Let's say that was our electron configuration, and now it would be krypton, okay? Right? And the highest energy level is what? 4, yes? Highest energy level is 4, and there are 2 electrons in an S and 6 in a P. Again, for 8 electrons in that highest energy level, being 4. Okay? So this is what an atom that has a fully filled p subshell looks like. It has 8 total electrons in its highest energy level. Okay? 2 in an s orbital, 6 in p orbitals, and this is called the octet rule. The octet rule says that atoms want 8 electrons in their highest energy level. That's what atoms want. They want 8 electrons in their highest energy level. The octet rule. Now, there's only one big exception to this rule. And Joe, you already sort of brought this up with helium, because helium has something equivalent, but it doesn't have a p orbital. It doesn't have any p orbitals, so it has what's called the duet rule. That if you could accomplish basically the same thing, a fully filled, fully satisfied highest energy level with either S's or P's, then it's functionally the same. So helium is just as happy as argon, is basically what I'm getting at. Does that make sense? Even though helium, it doesn't have any p orbitals, so it does not have a fully filled p subshell as its highest energy level, but it has something equivalent. And so that's the duet rule. That's the one major exception. But I want you to think octet rule, and when you hear that, I want you to think every atom wants 8 electrons in its highest energy level. And for that to happen, it's got to have a fully filled p subshell. Okay? Before we left, we talked about this last point, that atoms don't just want that, they will get that. And the way they do it is they either lose electrons and become cations, or they gain electrons and become anions. Okay, this is what atoms do. They want 8 electrons in their highest energy level, and they will lose electrons or gain electrons to make that happen. Lose electrons or gain electrons to make that happen. Do you remember talking about this? What is the charge on an electron? Positive or negative?
Negative.
Negative. So if an atom gains electrons, is it going to be negatively charged or positively charged? Negatively. So an anion gains electrons and is going to have a negative charge. Cations lose electrons and are going to have a positive charge. Okay? So cations are positively charged, anions are negatively charged. Of course, you'll remember the illustration I gave you that will always help you to remember the difference between the two, because cation makes you want to pronounce it cation, which sounds like vacation, and those are definitely positive experiences. Right? Unless you go on a vacation with your brother, which I guess all of you would that have a brother. No, but as adults, I went on a cruise with my brother. It was actually really positive. It was good. But I would never tell him that. So I hope he's not listening to this recording. What I told him, it was horrible and I'd never do it again. Because that's the way I talk to my brother. That's not true either. Nothing? It's not even Monday. You can chuckle. It's funny. It's hilarious even. Alright? So let's answer this question. Why are noble gases so happy? And the best way to answer it is because they already have what every atom wants. They already have what every atom wants. And atoms aren't like people. You know, people, they get what they think they want and they're still unhappy. Oh, you don't have to keep writing all that. That was just bonus information. But noble gases, they already have what every atom wants. Did any of you start writing atoms aren't like people? Okay. Right, people, you get everything you think you want and you're still unhappy because you just didn't know what you wanted. Right? We're fickle that way. Right? Although I know I want the Dodgers to win the World Series, but I don't think I'm ever going to get what I want. Maybe. They won the World Series when I was 1 year old. I don't remember it.
I think there's for 16
Yeah.
years.
So I know you haven't even had a World Series. At least I've had one. Alright? So noble gases, they have what every atom wants. That's why they're happy. So they don't really behave at all. They're very boring chemically. Because what other atoms will do to get there, they'll do some chemistry to get that, but the noble gases, they already have it. All right? Any questions about this question? That's a fun question to ask. All right. So our next question is this. Well, what happens when cations interact with anions? What happens? What happens when cations interact with anions? So as we take a look at the board, and let's say we take something like calcium. I mean, we already have it on the board, so let's do calcium, all right? True or false, calcium has 8 electrons in its highest energy level. False. It has 2 electrons in its highest energy level. Highest energy level is 4, and it has 2 electrons. So it has 2 options. It could either lose 2 electrons, or it could gain 6. And really it's even more complicated than gaining 6, because in between 4s and 4p, there's 3d. This is a little interesting, right? It's got to gain a bunch. It's not like weight, right? Where it's like, it might be easier to gain 6 pounds than to lose 2 pounds. Unless, of course, you have a hard time gaining weight. If you do, cherish it and hope it lasts forever. You know, I told this story to my class on Monday, but I got to share it with you. I had a guy, one of my former students, he came and lived with my wife and I for a little bit as he worked at the university. And, you know, he lived with us for about a year, and one time I was asking him, like, how can I be praying for you? And he's like, if you could pray that I would be able to gain some weight, that would be great. Because I've been working really hard, and I just can't put on any weight. I about near smacked him in the face. Said, I will not pray that you can gain weight. Like, drink a milkshake, you know? It's not that complicated. But apparently it is for some people. Cherish it. Alright? So for calcium, it's if calcium's gonna lose 2 electrons, it's not like it can just kick them out and they're just gonna float around willy-nilly in the atmosphere. It's not how it works. For calcium to lose 2 electrons, it's gotta find something to take them. Right? It's got to find something to take it. It's like when you have a dog. Like, you can't just kick your dog out of your house. I mean, you can, but it's against the law. Right? You got to find somebody to take it. Okay, so for calcium, it's much easier for it to lose 2 electrons than it is to gain 6. And really, it's way more complicated than even gaining 6, because you got 3D in between there. It's just it's bad news. Okay? So if calcium wants this, it's going to lose those 2 electrons. It will find some atom to take them. And it will lose those 2. Each electron has a -1 charge. So if it loses 2 electrons, what is its charge? +2. And so now this is calcium, either +2, although most chemists will write it this way. And I don't know why. I used to think it was because chemists didn't know how to read. But then I realized I'm kind of a chemist and I know how to read. So that can't be the case. So I don't know why. But anyways, so the electron configuration for calcium 2+ is identical to the electron configuration for argon. Because that's what every atom wanted. Calcium figured out a way to make it happen, but the only way it can make it happen is to actually now be charged. And so what happens then when something like this, calcium, interacts with something with a negative charge? Simply put, and this will be the answer to this question, is they form ionic bonds. A bond between a cation and an anion is called an ionic bond, which is wonderful because it's cation and ion, ionic bond. It's wonderful. Have you heard opposites attract? This is where this idea comes from. Because chemically and with magnets, which is also a type of chemistry, although arguably physics, opposites attract. Okay, and so this is the answer to the question we answered right at the beginning. Cations are naturally attracted to anions. Cations, again, they are naturally attracted to anions. Now it's a little bit more complicated than that because then we have to figure out a way where we can balance the charges. They will tend to bond in such a way to balance the charges. Basically, they will bond in such a way to where there's no longer any charge. Because if there's charge, it's going to keep on attracting the other charge. Right? Which is why humans are so attracted to lightning bolts. Because we're slightly charged. It's a little bit more complicated than that. Your cells are slightly negatively charged. The fluid around your cells is slightly positively charged, and so creates an electric field. But either way, it makes you like candy to a lightning bolt. Which makes playing out in a thunderstorm a little bit scary and slightly complicated. Unless, of course, you're studying lightning and then, like Ben Franklin flying a kite in a thunderstorm. But I imagine the string he was holding was not made of metal. It was just the keys hanging from the string to prevent him from being electrocuted. But he was still out in a thunderstorm, and he's likely as attractive as that key was. Anyways, another story, he survived. He also survived only sleeping like 3 hours a day. And he wouldn't even sleep it all in one time. He would sleep like an hour every 8 hours. Very productive man. All right. And so an example of this, by the way, this isn't how it is always going to work, but an example of this. A cation with a positive 1 charge will tend to bond with an anion with a negative 1 charge. That's not how it's always going to work. But this is an example of how this could work. So again, this is not how it is always going to work. So let's take calcium, for example. What's the charge on a calcium ion? Positive 2. But it's going to be attracted to more than just ions with a negative 2 charge. It'll also be attracted to ions with a negative 1 charge, or a negative 3 charge, or a negative 4 charge, because opposites attract. You'll just need different numbers of those materials to get it all balanced out. Alright? That makes sense? So let's take iodine for example. If we look at iodine does, true or false, iodine has 8 electrons at its highest energy level. False. How many does it have? 7. What is easier? For it to find something to take 7 electrons, or to it to find something to take 1 electron away from it? To take 1 electron away. And when it does, it will move from 5p5 to 5p6, taking on an extra electron. An extra electron has a charge of negative 1, giving iodine a charge of what? Negative 1. Okay? Now this iodine is charged. It is no longer called iodine. It is now called iodide. Because it's an ion. Wonderful. Changes name. And so these 2 ions are going to be attracted to each other. The calcium that has a charge of positive 2 is going to be attracted to this with a charge of negative 1 because they have opposite charges and opposites attract. But in order to balance this out, you're going to need more than 1 iodide. You're going to need how many? 2 of them. So if these actually form an ionic bond, you get something that looks like this. Calcium iodide. And we'll talk more about this as we continue to move on. After this week, I think we're going to talk about covalent bonds, and then we'll come back and we'll start talking about molecules and how all these things work and ionic compounds. And because really it's like, wow, this is beautiful. But this is overly simplified because anything that forms an ionic bond like this is a salt. And what do you know about salt? Can you see an individual grain of salt? Like an individual grain. If you take the salt shaker and you put it out, can you see an individual grain? Absolutely. Well, that tells us that there better be more than 1 metal and 1 non-metal, right? The table salt, we've seen this before, what is it? the table salt that we use. Sodium chloride, NaCl, which is 1 sodium, 1 chloride. But if it was only 2 atoms, do you think you could see it? Nope. So salts form these big crystals, and it's just in a ratio of 1 to 1, whereas in reality there are literally millions of them. More than millions. Okay, does that make sense? Okay, but we simplify it to just, write it this way. But then other things get a little bit, you could have individual molecules, but it's another story for a later class, okay? Are there any questions about this? So we answered it with the first point. What happens when cations interact with anions? They form ionic bonds. Okay? So let's do a couple of problems. And I pose this question, will they ionic bond? And the answer to that question will be yes, whenever what is true. What has to be true for the answer to this? For the answer to this question to be yes. What has to be true, Alex? They have to have opposite charges. One has to be positively charged, one has to be negatively charged. That's it. The magnitudes don't have to be identical. But if one is positively charged and one is negatively charged, the answer to this is going to be yes, they will ionic bond. Okay? So let's do this for magnesium and for sulfur. Sulfur we've already done before, it's over here, so we won't even bother doing this for sulfur again. We'll come over here and we'll say, true or false, sulfur has 8 electrons at its highest energy level. False. What does it need? It needs 2 more electrons, or it needs to lose all 6 of these. Gaining 2 is going to be easier. That's going to go from 4 to what? To 6. But in order for that to happen, it has to take on how many electrons? 2. Each one of them is negatively charged, and so it will now take on a charge of -2, or 2 minus for a chemist. Alright? But what about for magnesium? Now correct me if I'm wrong, but magnesium is placed in a position on the periodic table to where its electron configuration should end in 3s2. Is that correct? Yep, we've got a yes. And then a lot of quiet, so we'll say it ends in 3s2. And you guys at this point, if we're going to put electrons into the 3s subshell, what do we have to do first? Fill everything that's a lower energy level, starting with 1s, then 2s, then 2p, and then finally 3s. Okay? True or false? Magnesium has 8 electrons in its highest energy level. False. What does it need to do to attain that? Lose 2 electrons. It either needs to lose 2 or gain 6. It's going to be easier to lose 2 electrons. Each electron has a charge of what? -1. So if you lose 2 negative charges, what is your charge? +2. Okay, so magnesium has a +2 charge as an ion. So it is what? A cation or an anion? It is a cation, right? Cation, vacation, positive. Sulfur, it has a -2 charge. Anion or anion, right? You cut it, makes you cry. That's very negative. No? Did I tell you that after I told you that in class, I'd never once done this in my life. I went that night and I called an onion, an anion. And my wife did not think it was hilarious. In fact, she thought it was silly, but I thought it was funny enough for the both of us. And so I laughed plenty. Oh, it was great. Could you hand me that anion? She didn't find it funny. Anyways. So are these going to ionic bond?
Yes.
Yes, they will. And they bond in such a way where it's just a 1-to-1. Because the magnitude of their charge is the same. 1-to-1. +2, -2. Right? Magnesium, it's got $2. Sulfur wants $2. It's a perfect match. Right? It's like my children, except for they always want more than I have. But you know what? I give it to them, because I love them. That's not true, I don't give my kids anything. I feed them. But my son's like, Dad, I want to watch. So it's fantastic, get a job. But he's 5, so he can't. Alright. So will they ionic bond? Yes, they will. Magnesium and sulfur will ionic bond. Alright? Now let's do lithium and zinc. Alright. So looking at your periodic table, lithium should be in a position where its electron configuration ends in 2s2.
2s1.
2s1. Oh my goodness. 2s1. That's right, because 2s2 is beryllium. That was terrible. Y'all deserve better. So it should end in 2s1. And we've got to fill everything lower to put an electron into 2s. The only thing lower is 1s. And so that is 3 electrons. Is the number in the top right corner of lithium 3? It sure is. True or false? Lithium has 8 electrons in its highest energy level. That is false. And there's really only one way it can accomplish that, and that would be to gain 7 electrons. That is virtually impossible. Which means this is going to violate the octet rule. And I told you that there's really only one way to violate the octet rule. And what is it? To have the duet rule. So where you've accomplished basically the same thing by fully filling this 1s. Because now this energy level, it is completely filled. You couldn't put any more electrons in the energy level 1 if you wanted to. 2 is as much as it can take. It's hard as happy. It's like the stomach of a baby. It's smaller than that of an adult, so it doesn't take as much stuff to fill it up. But the baby's just as happy with a full belly as an adult is. Right? Man, that was a great analogy. That just came to me. Gosh. It works the same way too. You fill a baby's belly and it falls asleep. You fill an adult's belly and they fall asleep. Gosh. The only difference is we can talk and drive cars and cry when the Dodgers lose the World Series for the 2nd consecutive year. Although this year I knew they were going to lose, so I didn't cry actually. I was pleased to see them beat Milwaukee, and that to me, that was my World Series this year, because nobody was beating the Red Sox. I'm sorry if you thought differently, Micah, but nobody was beating the Red Sox. They were playing out of their minds. Anyways, so it loses 1 electron. What is the charge on lithium? +1. Right? It lost an electron that had a negative charge, now has a positive charge. Gosh, we're making great time. Now zinc. Correct me if I'm wrong, but zinc's electron configuration should end in 3d10.
Yes.
Is that right? If you're looking at your periodic table, is that right, Alex?
Or it is.
Well, so you know where 3d10 is, right? It's
Oh,
that
wait.
top D.
Oh wait.
Check in that last position. Is that zinc?
Yeah.
Oh yeah! 3d10. And now you know if you're going to start putting electrons into 3D, not 3 dimensions, but if you're going to start putting them into 3D, you've got to fill everything lower in energy. You've got to fill 1s, you've got to fill 2s, you've got to fill 2p. Oh my gosh, I need more space. You got to fill 2p, you got to fill 3s, you got to fill 3p, you've got to fill 4s, and then finally, you can put electrons into 3D. Right? That make sense? Just reading the periodic table, top to bottom, left to right. Any questions? Okay, true or false? Zinc has 8 electrons in its highest energy level. False, it only has 2. Its highest energy level is 4, and it has 2 electrons there. How does it get to 8? It loses these 2, or it gains 6. Which is easier? To lose 2. And it gets a little silly here when we've got these 10, we're like, what do you even do with that? It gets a little weird, and that's why zinc can make multiple charges. You can find zinc that is 2+, you can find zinc that is 1+, and I think you can even find zinc that is 3+. But all of them are positive. Will zinc and lithium ionic bond? No, they're both positively charged. So the answer to this is no. And what you'll find when you look over your homework is these 2 examples are actually given to you as 2 of the problems in the homework. You're welcome.